Okay, looks like you're back. Give you a second. And yeah, so it's these the Doppler issues are kind of built into the standard, right? So we figure out, okay, what's the maximum Doppler we're going to see out of cars and trucks moving and that type of thing, and design our standard around that. But this power, this peak to average power ratio, where our peak might be 10 to 20 times higher than our average power, is a big deal, and that's not easily solved. So, all right, I think I ended up pasting all this into another slide deck here that I've also uploaded to Moodle, since we didn't get there. All right, so we talked about these things. All right, so let's start talking about how all this comes into play in 5G. Right, so 5G is designed to operate in both traditional cellular bands, which we sometimes call FR1, and it's generally below 6 gigahertz, and on a practical basis above 450 megahertz. And but also because 5G is really pushing to try to get a lot more capacity out to the user, then we're adding these new millimeter wave bands up around 20 to 50, basically 25 to 50 gigahertz, and their bandwidth is no problem. We got tons of bandwidth up there, and so that eliminates that whole issue about capacity overall. But it does have some other issues. So it used to be just even a dream about doing 6 gigahertz in a consumer commercial market was crazy, and that was like military type stuff, right? But now that's routine, and someday this will be routine. These frequencies have kind of previously just been the domain of defense and that type of thing, but we're gaining electronics capability to generate and amplify signals and receive signals at these bands in a economical way. So yeah, the low bands are still dominated by concerns about spectral efficiency. We just don't have enough bandwidth for all the users that want to use it. The high bands are dominated by coverage challenges due to higher propagation losses. So it's just, you're going to have much higher losses at these millimeter waves, like when we try to penetrate through a wall, or just trying to send a signal multiple miles. And we've got to change our antennas, we've got to change our power amplifiers, all that. So just kind of the challenges in achieving high RF power efficiently at the current state of the art to overcome these higher propagation losses and that type of thing. It's pretty easy to come up with a 10 or 100 watt amplifier at 2 gigahertz. It's quite another deal to come up with a solid state high power amplifiers in these millimeter waves. It used to be we'd use traveling wave tubes and that type of thing, but of course that's not going to be practical for these type of applications. So some aspects of 5G are shared. Yeah, there was a question.
You said some of the FR2 bands are used in the military. You know any, like, which technologies by any chance?
So typically what's happened is that the military has used these bands for radar, and also in some cases for satellite communications. And so satellites are the same type of issue. They're very expensive to build and to launch. And so you want to get as much bandwidth out of that resource as you can. and but they're not huge, so we don't have room for big antennas and that type of thing. So that's kind of meant that satellite communications are best done in these millimeter wave ranges. The so as militaries throughout the world have gotten more efficient at using their spectrum, it has opened up an opportunity to move that spectrum to commercial use. These things are kind of coordinated. Maybe we'll talk a little bit about this on Tuesday with standardization, but frequencies are ultimately coordinated by your local jurisdictions in the US. That's the Federal Communication Commission. And there's also the NTIA, the National Telecommunications Infrastructure. And I don't know. Basically, the NTIA is responsible for government purpose communications, and the FCC is for everyone else. In the UK, it's Ofcom, OFCOM, and so every country has their national regulator, but then they also get together at World Radio Conferences or WORCs, where they kind of hash out, all right, let's everyone try to use 2.45 gigahertz for wireless networking type thing. It's actually what's called an ISM band, or industrial, scientific, and medical type things. And so there's some harmonization around the world, but so these frequencies here, the point I'm trying to make is that they're not all available, and certainly not all available yet. But 5G has got its eyes on them, and some bands are available in some areas. So that's what's going on there. So yeah, so some of the aspects of 5G are shared between bands, while others are more relevant to a specific band. And when I say band, it's the low band or the high band. So there's some design issues that we've tackled in 5G that are really just for kind of that millimeter band, and others that are really just for the low band. But there's a lot that's trying to cover both bands. The goal has been to try to come up with a single standard with enough options that we can get economies of scale. So when you're building hardware, when you're writing software, it can be used in as many different applications as possible. All right, so 5G uses OFDM on both uplink and downlink. That's in contrast to 4G, which uses OFDM, and 4G is LTE, right? And also it could be WiMAX, but we'll just talk about LTE. So 4G uses OFDM on a downlink, and it uses this kind of similar but kind of not type of waveform called single channel FDMA on the uplink, which is a little easier on the power amplifier, but yet requires supporting yet another waveform and all. So 5G is kind of moving to FDM on both the uplink and the downlink. The OFDM symbols are arranged in a resource grid in both time and frequency as slots, which are composed of a number of different symbols, subframes, and then frames. So a frame is about 10 milliseconds long, and it's got 10 subframes in it. And each subframe has a bunch of slots, and each slot has a bunch of symbols in it. Okay, and each symbol has a bunch of subcarriers in it, right? So do I have a grid? I guess I didn't get a grid pasted in there. But you can, I think I had it in a previous lecture, maybe Tuesday's lecture, or maybe last Friday's lecture, where there was kind of a grid, and on the vertical dimension was frequency, and then the horizontal dimension is time. So these subcarriers have been talking about in 5G, they can vary because we're working on over such extreme differences in overall frequency and bandwidth. So we start with subcarrier spacing of 15 kilohertz. So each of those little subcarriers are going into that IFFT block are 15 kilohertz, and that's what's being modulated. But you can also have 30, 60, blah, 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 using this little formula, 15 times 2 to the n. So these go up in powers of 2, right? So the OFDM symbol duration. So there's a little bit of legacy here in that there was some sampling times that were standardized in CDMA and 3G and GSM also, and WCDMA and all these older type of standards. And there's a lot of signal processing hardware and firmware that's being developed using those sampling times. So that there's some legacy that kind of folds into this. But when we take these subcarriers and we get a bunch of them, we do this IFFT, then our with this kind of standardized sampling time, then our OFDM symbol durations are going to kind of start at 66.7 microseconds long, right? But then as we go to wider subcarrier spacings, we end up going to narrower OFDM symbol durations. So this kind of translates into maximum system bandwidths of kind of nominally 50 megahertz, a maximum with these type of values, right? And but it can go up to 400 megahertz. In LTE, our waveform bandwidths were more of 10 megahertz, 5 megahertz, 10 megahertz, and in some cases, some vendors were able to support 20 megahertz or so. So we see with 5G, we're really jumping up a lot in bandwidth, and part of that is advances in analog to digital converters. It's constraint to be able to build an ADC at wide bandwidths, high sampling rates, and still have enough bits of resolution to support high order modulations like 256 Comm and stuff. So really it's the improvements in silicon technology that's allowing us to go to these wider bandwidths. Cyclic prefix that we talked about earlier, these are a fraction of the OFDM symbol duration. So there's actually both kind of a short and a long cyclic prefix. The idea with setting the cyclic prefix is that it should be long enough to cover the delay spread in a typical channel, right? So if the variation between the different rays reaching the receiver, if some take 100 nanoseconds longer than the others, maybe 900 nanoseconds longer, something like that, right? So it should the cyclic prefix should be longer than that delay spread, not too much longer, and we can maybe sacrifice a little bit, but it should be on that order, right? That's what's governing the length of your cyclic prefix. Remember, this helps us decode this without having to do all this crazy equalization or compensation of our waveform, but it also is wasting time and energy. So we don't want to go too long, but it needs to be long enough to cover kind of that delay spread of reflections from the minimum delay to the maximum delay. All right, so our maximum FT size is 4096. Compare that to LTE when it was more 1024, 2048. Of course, these are powers of 2 because the FFT algorithm works best most efficiently with powers of 2. And as I said, a lot of those are set to 0 as guard bands. So only 3,300 are actually used. There's also a lot of timing synchronization that has to go on in these waveforms, and signals that are help the receiver to calibrate and equalize the channel. Even though we have a CP, we still have to do some equalization, and so there's some known reference signals embedded into the system, and also that affects the number of used subcarriers also, right? So the modulation of each subcarrier can range from BPSK all the way up to 256 QAM. LTE, I think, capped out at 64 QAM, I think. And you, as you might imagine, this is a lot of control signals are really at a higher level of the network stack, and we're not going to be able to talk about that in this course. It's maybe a different type of course, but you can imagine that there are signals that are very, very important in the LTE waveform, the communication that's going on, and those can't be missed, right? So if the base station is telling the handset or subscriber unit, hey, you should use 64 QAM, and you should transmit in this slot of subcarriers and time, that's got to get to that handset reliably, right? And so we're going to use BPSK or maybe QPSK for a lot of those important control signals, what we call the control plane. And so as you look at the standard and as you kind of go up from that radio level up the network stack a little bit, you'll see that there's all sorts of different things defined on how the base station and the subscriber units kind of collaborate to communicate, right? And there's all these flexibilities, all these subcarrier spacings, these cyclic prefix lengths, and all these things, right? So we've got to collaborate on those and understand, yeah, what I'm supposed to be using. So all those signals are exchanged over what's called the control plane, and those are basically just well-known areas of the overall frame that that are for this purpose. Yes, there's a question.
Yes. So I don't know if I understood correctly. You were saying that some of the controls signals are sent as like BPSK or QPSK. Is that to the handset?
Yes, and potentially from the handset back to the base station also. The point being is that those modulations are the most robust to errors, right? We think way back, like before the midterm, when we were looking at calculating error probability of binary antipodal modulation, and that's another word for BPSK, right? And we found that had the best error immunity and stuff. So if you're just have a voice signal, well, if I get a few samples wrong, it's not that big a deal. Our human ears kind of wash over that, and unless it gets really bad, we can still understand things, right? But if there's a control signal, we've got to make sure that is received as well as possible, right? I mean, there could still be an error, but we want to make sure that we've done the best job. So
my question was just about so the handset recognizes the scheme being used for each symbol, like, because you can send a symbol from any of those schemes, it sounds like.
Yeah, so yeah, the standard is set up so that there are well-defined subcarriers and times within an overall frame or subframe or slot that certain information is sent, whether it's synchronization symbols or reference signals or control plane signals and that type of thing. So these are allocated to these purposes. And then there's also headers in the system that can tell the subscriber unit, hey, here's some other control plane information, look here, right? And then it will also tell it, and this is then where the rubber meets the road, so to speak, is that here is where your data is located, right? So the base station is going to make a transmission, and it's going to send out a frame of data, and that's going to include let's see, 10 times 14, 120, maybe 100 or so OFDM symbols, right? Each of those OFDM symbols might have 3,000 subcarriers in it that have data in it, right? So it's broadcasting that out, and each subscriber unit has got to understand, where is my data located versus the guy sitting next to me. His phone is getting data too, right? But it's in a different place in that frame, in a different subframe or slot or subcarrier, that type of thing, right? And so there's information sent in these well-known locations that then point to other locations where the data is. So this is where the whole art of electrical engineering blurs with computer engineering and computer science, because there's a lot of networking concepts here with packets and headers and that type of thing that is traditionally taught to computer engineers and computer scientists, and maybe kind of washed over on electrical engineers. But you see that there's a ton of overlap here, right? So all right, so hopefully that kind of clears things up. Maybe I'll let's see if we have time. Maybe I'll cover that on Tuesday. I'll try to illustrate this a little bit more. So in 5G, we have these this idea of a resource block. So that would be 12 consecutive subcarriers in a frequency domain, and that is kind of the minimum block that can be scheduled to individual subscriber units. So if I'm going to allocate a certain number of subcarriers to talk to some guy named Joe, right? Then I can do that at that granularity of 12 subcarriers, 12 consecutive subcarriers. I might allocate 12 to them. I might allocate 24 or 48 or 36 or something like that, right? But I'm going to do that at a granularity of 12 consecutive subcarriers. Why don't we go down to one each subcarrier? Well, all that signaling gets more verbose then, right? So if I'm divvying up 4096 subcarriers by 12, okay, I need a certain number of bits in my packet to describe which of those 12 groups are yours. But if I'm having to go all the way down to each individual subcarrier, I need even more bits. So I'm using up space in my packet just for this kind of control plane type information. So we just kind of draw the line at 12 subcarriers as that granularity. And that means that sometimes maybe I only needed 10, but I've got 12. Well, there's 2 subcarriers that might be going to waste, so to speak. But that's a trade-off without having to increase our address space in trying to describe to that subscriber unit exactly which subcarriers are being used, right? There's also primary and secondary synchronization symbols. We call those PSS and SSS, and they are in that overall frame. I think as we mentioned that frame is 10 milliseconds long, and that includes a whole bunch of OFDM symbols, right? Organized in slots and subframes. And so at the very beginning of that frame, and then somewhere in the middle, the very beginning has this primary synchronization symbol, and in the middle has the secondary synchronization symbol. And these are signals in a very specific code that are always the same, and for a given base station. And the receiver can look for those, right? And it can constantly be looking for those PSS and SSS well-known symbols. And when it sees those, that's how it figures out, hey, a frame is starting now, and it's starting exactly now. So the PSS helps kind of, it's a coarse search, it kind of helps it gets kind of aligned, and then the SSS helps it really kind of refine that timing and keep timing throughout that whole 10 milliseconds, right? So we might be sampling at, 30 megasamples per second or something like that, right? But we're needing to maintain precise timing over 10 milliseconds, and that's what these synchronization symbols help. So there's a lot of other reference symbols. These are well-known signals in the standard that are at a particular amplitude and phase, and they're there to help the receiver kind of align and equalize out any effects in the propagation channel. All right, a few more minutes left. So real quick, talking about 5G MIMO modes. We've kind of spread this MIMO lecture over 3 different lectures now, but the MIMO that we had been talking about before was the idea of we're going to kind of compensate for the channel and try to combine these different rays that have different delays and amplitude coefficients associated with them. And we're going to try to linearly combine those in a receiver, or maybe pre-code them so that by the time they get to a receiver, they happen to be combined, aligned and combined. So there's a number of other levels of sophistication on what we can do when we have multiple antennas. And a classic one is this one that's was developed by this guy Alamuti, and it's known as an orthogonal space-time block code. So sometimes abbreviated STBC or OSTBC. These are going to be more common in the low bands. In the high bands, I think I have another slide about that. So I'm just going to give you a real quick example of this. And so the idea here is pretty cool ideas, and we're going to send out symbols over 2 periods, right? So if we're sending out something over a single period, then we're going to take that and kind of replicate it over 2 periods. In the first symbol period, we're going to send this S1, whatever that is, right? This is not unique to OFDM or whatever, but we're going to send symbol 1 on the first antenna, and then symbol 2 on the second antenna simultaneously, right? So normally we'd send symbol 1 first and then symbol 2 next. In this case, we're going to send them simultaneously, but on separate transmit antennas, right? And by the way, when we talk about separate transmit antennas or receive antennas, that also means that they have a whole separate RF chain. RF power amplifier, local oscillators, mixers, all that, right? And so our signals are really different that are being sent on these things, right? Even digital analog converters, analog to digital converters, whatnot. So, all right. So in the first time period, we're going to send each symbol, but on separate antennas. In the second period, we're going to send minus the complex conjugate of symbol 2 on the first antenna. So we're going to swap antennas, and we're going to send the complex conjugate of symbol 2, but we're going to take the negative of that. And then on the other antenna, oops, I should have had a subscript of 1 on this one. We're going to send the complex conjugate of S sub 1 on the second antenna, swapping antennas at different time periods and doing this kind of complex conjugate along with a negative sign, but only on S1, only on S2, I'm sorry. So mathematically, we can kind of draw this out. Our receive vector is going to receive Y1 and Y2, and it's going to take that symbol vector of S1 and S2 and multiply it by the estimated channel, and it's going to get scaled by power. There's going to be some noise along with it, right? So our channel here now is going to be both H1 and H2, but then it's going to be kind of this H2 star and minus H1 star with kind of reflecting what we're sending here, right? And so that's we know that S is this S1 and S2. So when we go through this, we're going to end up with this Y. If we received Y, we multiply that by this Hermitian of which again is a matrix form of a complex conjugate. And when we do that, we also do a transpose of the matrix, right? So I know we haven't done a lot of examples of that, but anytime you're dealing with matrices and doing a complex conjugate, you're likely doing a Hermitian, which involves this transpose. So we end up with Z's as estimates that are now separating out these symbols, and we use Z because there's some noise that gets carried in. These S's are now scaled by this Frobenius norm. Again, that's like squaring the elements and adding them all up. So this ends up being a scalar. This is a scalar. So that's a vector multiplied by a scalar. So we get a scaled version of S at the output. So it's been separated out. But we get this scaling by these two different antennas. And yeah, we got some noise, it's scaled also. So anyway, that's the Alamuti type encoding. So our low bands use these similar type of MIMO techniques, and there's a handful that are in the standard that are optional options to use. In the high bands, we're really emphasizing beamforming techniques. So they're we're using antenna theory to try to form directional antennas, so we can point that beam towards the user. But well, maybe we don't exactly send it towards the user. Maybe we try to figure out that propagation environment and send beams along those rays that might be reflecting towards the user. And while we're at it, let's see if we can form a null towards any interference sources. So as you can imagine, that's fairly complex, especially when these subscriber units or the interference are moving, they're time varying, therefore, and we're trying to do this over a wide bandwidth. So there's a lot of challenges associated with that. So if you want a good start to your career, that's a great area to work in. Finally, our 5G channel coding. These are low density parity check codes and also polar codes. They're more advanced than what we have studied, but are kind of, these low density parity checks are like a sparse linear block code, but they're solved iteratively, and that's all we're gonna have time to talk about. I'm sorry. So let's talk real briefly about some no, we'll wait for Tuesday to talk about this, but it's up on Moodle, and so you can look through these last few slides over the weekend and Monday, and then on Tuesday we'll talk about cellular concepts real briefly, and then talk about standards and research directions, and then next Friday will be a review. So, all right.
Thank you, Professor.
There will not be any more homework or labs. So in case I wasn't.
Is there another homework?
No, I don't think so. I think people are generally doing good on homework. I know there's a few that really haven't, whatever reason, I get it. They've made some decisions not to do all the work and that type of thing, but I think generally the homework people have done pretty well on. So I don't think there'll be any more homework. So
Sounds good, Professor. All right, you have a nice one. Enjoy your weekend.
figure